Hello, everyone. I'm Kai Yao. It's my pleasure to present our work, Efficient Set-Bounded Community Search over Large Networks. Networks are everywhere, like social networks, web graphs, citation networks, and biological networks. Community search is a fundamental problem in graph mining. Here is a general definition of this problem. Given a graph G, a query vertex Q, find a cohesive subgraph containing Q. For example, the subgraph in the circular area is a community containing Q. Community search has many applications like event organization, recommendation, protein complex detection, and advertisement. Most of the existing studies ignore the size of the community, yield communities of very large size, which may overwhelm end users. Here is a comparison for community search solutions on Govala. We can see no matter which metric is used, the size of the community is large. Limiting the size of the returned community is natural and interesting from an application point of view, like organize a hiking trip with up to 15 attendees, assemble a team of up to 10 workers for a project. So in this paper, we study size-bounded community search. Here is a formal definition of this problem. Given a graph G, a query vertex Q, and a size constraint L to H, SCS problem aims to find a subgraph H satisfying following conditions. Firstly, H is connected and contains Q. Secondly, the number of vertices in H is at least L, but at most H. Lastly, the minimum degree of H is maximized among all subgraphs of G satisfying the above two conditions. We use minimum degree to measure the cohesiveness of a subgraph. For example, we say the second graph is more cohesive than the first one. Let's see an example. The query vertex is V1, size constraint is 4 to 8. This subgraph is a feasible solution. This subgraph is the optimal solution with minimum degree 3. The whole graph has minimum degree 3, but it does not satisfy the size constraint. SCS problem is NP-hard. To solve this problem exactly, we resort to branch and bound algorithm. Firstly, let's see a basic enumeration algorithm. The main idea is to enumerate all feasible communities and identifying the one with the largest minimum degree. We use capital C to denote the intermediate solution set. We use capital R to denote the remaining set of candidate vertices. Then select a vertex Vi from R and generate two enumeration subspaces. Move Vi from R to C, discard Vi from R. Then conduct a recursion on each of the two enumeration subspaces. Note that we use H to maintain the currently found best community. When C forms a feasible solution and is better than H, we update H. Let's see an example. Suppose the query vertex is V1, size constraint is 3 to 5. The enumeration process can be depicted as a binary search tree. However, there are several limitations of this basic enumeration algorithm. Large search space, no pruning-based upper bound, naive branching rule. To solve this problem efficiently, we propose the following techniques in the paper: reducing techniques, upper bounding techniques, domination-based branching. In this presentation, I will only introduce the upper bounding techniques. The main idea is that given an instance CR, we compute an upper bound K bar of the minimum degree of all feasible communities derived from this instance. If K bar is no larger than K tilde, prune this instance. K tilde records the minimum degree of the best community we have found so far. We design two upper bounds: neighbor reconstruction-based upper bound, degree classification-based upper bound. Firstly, let's see neighbor reconstruction-based upper bound. it selects this number of candidates with the most links to C. For each selected candidate, reconstruct its links to C. That is, change its links to vertices in C that currently have the smallest degree. Finally, the minimum degree of vertices in C is the upper bound, UNR. Let's see an example. Suppose the query vertex is V3, size constraint is 5 to 8. The colored vertices are in C, and the other vertices are candidates in R. Firstly, we select top 3 candidates with the most links to C. They are V4, V9, and V0. Then we make reconstruction for V4. That is, change its links to the vertices in C that currently have the smallest degree. Then we make reconstruction for V9 and for V0 in a similar way. Finally, we select the minimum degree of the vertices in C as the final upper bound, 3. The next upper bound is degree classification-based upper bound. It classifies the vertices in C according to their degrees. C tall contains those vertices in C whose local degree is no larger than tall. For each tall value, we derive UNR tall, which is the same as UNR with 2 differences. It only considers vertices in C tall, and it selects this number of candidates with the most links to C tall. Finally, it returns the minimum UNR tall as the final upper bound. Let's see an example which is same as the previous one. Firstly, we classify C into different sizes. Then we use C1 to derive UNR1, which is 2. Then use C2 to derive UNR2, which is 3. And also, we derive UNR3 as 3. And finally, we select the smallest one as the final upper bound, 2. Next, let's see experiment. We evaluate the following algorithms, GreedyF and GreedyD, 2 heuristic algorithms proposed in another paper, which are solving the same problem as ours. SC-BRB is our branch and bound algorithm equipped with all the proposed techniques. All algorithms are implemented in C++. The table shows the datasets used in our experiment. Firstly, its effectiveness evaluation. We evaluate the minimum degree and the edge density of the returned communities under the size constraint of 9 to 12. We can see SC-BRB has the highest result quality. Next is efficiency evaluation. To evaluate different techniques used in our algorithm, we evaluate the following algorithms: SC-BRB without reduction techniques, without upper bounding techniques, without domination-based branching. We can see each of the techniques contributes to the efficiency of the SC-BRB algorithm. Next is a comparison with PSA, the progressive algorithm proposed in another paper for approximately computing a minimum K-core. We report the performance of PSA with different approximation ratios, 1.2 and 1.01. We can see SC-BRB outperforms PSA 1.2 in terms of both result quality and running time. PSA 1.01 has the same result quality as SC-BRB due to the small value of approximation ratio, but it's much slower than our algorithm. Finally, let me make a conclusion. We studied the problem of size-bounded community search. We propose a branch, reduce, and bound algorithm, SC-BRB. Extensive experiments demonstrate the effectiveness and efficiency of our algorithm. That's all. Thank you.